In this video, we'll continue our discussion of vector fields by determining if a vector field is conservative, and if it is, determining the potential function while focusing on curl. So we know if the curl of f is 0, then f is conservative. All right, so that just comes from the definition of curl. So curl is, and I'm going to skip the definition with the cross product for a moment. I'm just going to show the end result, which is the partial p with respect to z, not z, but let's see, I got it right here, y minus the partial of n with respect to z, I, minus, okay, the next one is mz, m with respect to z, minus p with respect to x, j, and then plus, and then our last one is n and m, so the n with x and m with y. Okay, what that really says is if the curl is 0, we can write out this definition the way it is here. We could put that the partial of p with respect to y is would be equal to the partial of n with respect to z. That would be if we wanted 0, right? If those two are the same, then this subtraction would be 0. We also want the partial of m with respect to z to be equal to the partial of p with respect to x, and then the last one's n with respect to y equals m with respect to, we have that backwards actually. That should be x, and that should be y. Notice that these are just every combination of m, n, and p, and then we switch the associated variables, like m here, n here, and p here. M is the I, so it goes with x's. N is the j, so I associate it with the y. And p is with k, which I associate with z. And then these three equations are every combination of m, n, and p with their variables flipped. So we just have to show those three things to show that it's conservative. So p with respect to y is just going to give me an x. N with respect to z is just going to give me an x. We're good there. M with respect to z is just y. P with respect to x is just y. Good there. N with respect to x is just going to be a z. And then m with respect to y is just a z. Then we have that f is conservative. All right, since it's conservative, then we can work backwards to find a potential function. All right, so I'll shrink that down. So since that is true, then I'm going to use some math lingo here. There exists a phi such that the gradient of phi is equal to f. That's the definition of conservative, right? I use some math language here. This is there exist. There exist. And then this is such that. Right, that's just math lingo. Then there exists a phi, which is a function that's going to be our potential function, such that the gradient of phi is equal to f. I'm going to write that what that means with respect to phi. Well, that's just the partial of phi with respect to x. That would give me my I component. And then my y component would be take the partial of phi with respect to y. That's the definition of the gradient. That's all that is. And then, we have a third component in this one. That was y. And then partial of phi with respect to z. So that's the definition of the gradient. And I know that's equal to m, n, and p, which we have right up there. So phi of x, y, z is going to be equal to the integral of m dx. All right, or we could call that the partial of phi with respect to x. That's going to be m dx. There we go. So I just put m there. All right, m is 3x squared plus yz dx. All right, so I go ahead and I integrate. I go up by 1, divide by my new one. So this is x cubed. And then that doesn't have an x, so I'm just going to introduce one. And then now we have a function of y and z. All right, so phi is equal to xyz, or sorry, phi of xyz is equal to x cubed plus xyz. I just like writing it down here because I'm going to do something with it right after. So I like to have it in line. There we go. So if that's true, then we can take that derivative with respect to y, the partial, and we're going to get xz plus, and this is going to be dh with respect to y. Well, that's the same thing as if we look at here, this is our definition of n, right? So I just grab n, that's the very top here. That's going to be 3y squared xz, 3y squared xz. And now notice xz is on both sides, so I have dh dy equals 3y squared. Well, I can integrate that. So h of yz, well, I just integrate with respect to y. I go up by 1, divide by the new one, so that is y cubed. But I also have one more variable, that's going to be a g of z. So if that's true, I'm going to write out phi again. All right, phi is equal to x cubed plus xyz plus y cubed plus g of z. So now it would make sense to take the partial of phi with respect to z. All right, the only thing that's going to stay is going to be an xy, and then plus g, the partial of g with respect to z. And we know that's going to be equal to p by definition. And p is equal to 3z squared xy. 3z squared plus xy. You can see that they're gone there. All right, so we have dg, dz. The xy's are gone. I got 3z squared. And then all I got to do is take that the integral to go back to get my g. So we have that g of z is going to be equal to z cubed. And then plus, we have a constant that could be there. We've taken care of all variables, though. All right, integrating gets us that. Let me shrink this down just a bit so I can make room for our final phi. All right, so phi of xyz is equal to x cubed plus xyz plus y cubed plus z cubed plus c.